Was this the USB or something? Or?
We actually need to get one. We fortunately only have this like bamboo stick for the time being.
I can work with this.
All right. Just gonna need another minute, and then I'll be good to go.
And if anyone steps on you, whacking it.
Yeah.
I'm not saying you should. I'm just saying it's a possibility.
Okay.
Check me, Simon.
All right, we're almost good to go. And sorry, you are sharing your screen right now?
Hang on.
Okay.
We'll do that for a moment.
That's the last check, and then we should be good to go.
The camera is turned off at the moment.
Yeah, you don't need to have any of those from Zoom, camera, or audio. Just screen share for your slides.
Okay.
I say as my audio is turned on. All right.
Can you see the screen?
Yes. Okay. Full screen. All right. I will introduce you in a moment. Just one sec. Okay, that's looking good. I know we're like a minute or two behind here, guys. Sorry. Just a little bit more setup to do for the first talk.
Should we wait for like legitimate questions for the end of the thing?
It's up to you.
It's probably best that all
Sure.
questions can be at the end.
Sure.
That's a good idea. All right. Check. Yeah, okay. I think we should be good to go. So thanks everyone for coming. Our first speaker, we're gonna have two, and then we'll have a break. Confirming the schedule. You can grab snacks, tea, or anything, and then come for other talks or switch rooms to 606 if you want. So yeah, let's welcome our first speaker. Round of applause.
Good afternoon, everyone. Thank you for coming to my talk today. I will be talking about the growth and characterization of bismuth palladium oxide crystals. This project was not made would not have been possible without the help of my graduate student supervisor, Julian, and I am doing this project as part of the course Physics 379. I will be having my oral exam. So, to start, so here's a brief overview of what I will be talking about today. First off, I will be talking about why I chose bismuth palladium oxide in particular. Then I will talk about my methods, and I will talk about three key results. First off, I will be talking about my bismuth palladium oxide growths. I will be talking about X-ray diffraction, and lastly, I'll be talking about how the behavior of bismuth palladium oxide, namely the change in resistivity across temperatures. So, we can take a look at this. We can start by explaining why in particular we're picking palladium oxides. As you can see, one thing we can pay attention here is the periodic table, and copper is known to have a high D value. As you can see, it's quite deep in among the transition metals, and palladium is known to have a comparable hybridization, and by the way, as D increases, copper has the highest orbital hybridization with oxygen, and Palladium, it only prefers a four-folded coordination, and covalency, it's the similarity of the energy levels, is what forces this coordination. As you can see, copper 4, palladium 2, silver 4, platinum 2, they have similar energy levels, which is why most of them form this planar four-folded coordination. Another thing I'd like to talk about are the basic facts of superconductors. One thing to note is that resistance drops to 0 at a critical temperature, as you can see here. And another thing to note is the behavior of a non-superconductor. The resistance steadily decreases until it reaches absolute 0, but for superconductors, it jumps to 0 at a critical temperature. And there are a few high-temperature superconductors that are already in existence, such as yttrium, barium, copper oxide. Most of the superconductors we know are for low temperatures. When I say low temperatures, we're talking about temperatures about 4 Kelvin or even millikelvin. But I'm focusing on palladium oxides because of its insulator to metal transition. Among these, all these things, we have decided to pick bismuth palladium oxide because of its low palladium distance. You can take a look here. These black dots. They have lower palladium distance compared to these other palladium oxides, and they have lower resistivity. For instance, especially for this one in the bottom here, this is a dope bismuth palladium oxide doped with lead, and as you can see, it has a resistivity in the order of 10 to the -1 or 0.1 ohm centimeters, and on the other hand, for bismuth palladium oxide, the undoped one, it has a resistivity of 316 ohm centimeters. And because of this, and for these in mind, my study focuses on the increasing of conductivity for bismuth palladium oxide by doping this with lead. Another thing here is you can pay attention to is the band structure. So what I'm trying to do here is that I'm trying to shift this Fermi energy downwards. There's this flat band here, and this is another way of saying that the electrons are localized. So how I conducted this study is that I started off with the growth of bismuth palladium oxide crystals. So what I did is that I measured bismuth oxide, palladium oxide, and lead oxide for each x. According to this equation, if you all know your balancing chemical equations sort of thing, this should be familiar to all of you. After I measured these, I ground them all together. And once that was done, I did an initial salt flux growth with sodium chloride, heating it up according to figure 1. So as you can see, I heated it up to about 825 for about 5 hours, then held it at that temperature for 2 days. The reason why I did this is because salt, particularly sodium chloride, when it melts, it pushes the atoms around, and sodium chloride is a catalyst, meaning it speeds up the reaction process. And once that was done, these salts harden up again, and I dissolved them by using some distilled water. And once the powder is dried up, I pelletized it, then heated it up again, this time according to figure 2. So you can see here, I heated it up the way to 730. Then I heated it up at a lot slower rate, up to 850. Then held it there for 12 hours, then cooled it down and get back to 730. I also attempted calcium oxide doping, but that's not what I will be talking about today. So, let's move on to the results. One of the things that I will be presenting today are my bismuth palladium oxide undoped single crystal growths. One thing you can notice here is that these look like needle structures which have a length of a few millimeters all the way up to a centimeter. And the reason why these form is that at a certain temperature, the molecules begin to clump, and that's what causes these crystals to form. There needs to be the perfect recipe for that. If you put up the heat time too long, then these molecules start to separate, and then the crystals disappear, and you don't get those. My next key result I will be talking about today are my X-ray diffraction patterns. So as you can see here, so basically how this works is that I have an X-ray regime, and then it's put through a slit, and then basically the sample reflects across different angles. That's the general idea behind X-ray diffraction. But essentially, one thing to note is that for X-ray diffraction, whenever we're doping, adding some dopant will shift the peaks to the left. The relative intensity is not really of a matter here, but as you can see for the indoped sample, the peak is about at 29.25. But then, as I increase the dopant, it moves to the left. And there's also one thing you can notice that for 0.3 and 0.35, there are these new peaks that were not present in the other doped samples, which suggests that x equals 0.3 is the solubility limit. And when I say solubility limit, this means that the lead oxide is no longer incorporating with the bismuth palladium oxide. And then you can also take a look here for the scattering angle at between 30.1 and 30.15. There's a peak here, but then it's shifted to the right for these scattering angles. After this, I measured the resistance of these bismuth palladium oxide samples through temperature. I did a 4-terminal measurement because I'm measuring some small resistances. And if you have small resistances, this is what you want to do, because that reduces the contact resistance, which is already present in many of our circuits nowadays. So the voltage is measured through here, and that's what I was taking. And from there, there's already a fixed current going through, and I was able to get the resistance from there. In order to do that, I put my sample into this probe. This is from Professor Stephen Julian's lab, and basically what I did with this is that I dipped this into liquid helium so that we can get to 4 Kelvin, which is the boiling point of liquid helium. I also did my resistance versus temperature. As you can see, the resistance does not change a lot for x equals 0.1, as you hear right here. It remains in the order of 10 to the -2, and one thing to note is that I measured resistance and not resistivity. You can also take a look at the resistance graph, especially for undoped samples. The resistance is on the order of mega ohms, but then here we're just on the order of ohms. This implies, because of the low resistance, this implies that for x equals 0.1, it is almost like a metal. But then when we get to 0.2 and 0.3, it has a the maximum resistance at the temperature of the boiling point of liquid helium of around the order of 10, which we don't know. It might return to an insulator. I also did a Mott variable range hopping. So variable range hopping is the hopping of the electrons that from one side to the other when a current is drawn, and that's what's going on here. So basically I fit this to the function where sigma is conductance, and then sigma naught and T naught are some constants that were done in the curve fit, and then T is the temperature, and basically D is the order. If we're talking D equals 0, then that's an ordered semiconductor, and if D equals 2, then this is a disordered semiconductor. I attempted the fits for D equals 0, but I found out that D equals 2 had the best fit. As you can see, it tended to fit it pretty well. As you can see, the red line is my fit, and then the black dots correspond to the data. But one thing to note is that it's pretty interesting. My fitting parameters did not really fit very well, but I will be testing this a little bit further. But basically, might tend to fit a little bit better for d equals 0 compared to d equals 2, which may suggest it could be an ordered semiconductor. One thing I also did was that I attempted to truncate the data between about 60 to 100 Kelvin, and it tended to fit a lot better if I truncate the data, but it still did not fit. But again, I will fix this up as part of my preparations. But this may suggest that it's an ordered semiconductor. To summarize, I successfully grew undoped bismuth plate oxide crystals, and this looks promising. We are looking to measure them, measure the X-ray diffraction with these. And another thing is that the lead oxide dopant of X equals 0.1 produces a nearly metallic state, and X-ray diffraction shows peaks shifting for higher dopants, especially for X equals 0.3. Those are the ones that's the solubility limit. For the next steps of this project, I am considering other dopants with an oxidation of 2+, state of 2+, like tin. The reason why we're not working with lead and calcium, for lead, it's highly toxic. We already know that. And it has a larger ionic radius compared to bismuth, 3+. And the fact that it has a larger atomic radius means that it's going to shift the whole lattice further, and that's what's causing to increase the resistivity. We're also not doing calcium because it is not electronically active, and that it has a lone s electron pair. Another thing we're doing is that I will be redoing the growths with the lead oxide and considering other doping levels like x equals 0.05, x equals 0.075, x equals 0.125. And the reason why I'm picking these is because x equals 0.1 had a low resistance compared to the other doping levels. And we are trying to find the absolute minimum of resistance when these samples are cooled down to the boiling point of liquid helium. And lastly, I want to grow larger single crystals for dope samples, as my previous growths have been small, and we are looking to improve our growths. So yeah, that's all I have to say about my talk. Thank you for listening. I'm now open to questions. Yes.
Now, this one's more or less just like going into the future about like this experiment and whatnot. Once you get to like the desired results and whatnot, what doors can this open up to in terms of like superconducting?
That is a good question, honestly. So, a thing about superconductors is that we're not exactly sure that they're superconductors. We're more or less interested in the insulator to the metal transition, and superconductors, they tend to be quite similar because there exist copper oxide superconductors, and there's the insulator to metal transition. Cool. Does anybody have any other questions? Yes.
What advice would you give to undergrads that are interested in doing this kind of work? Like courses to focus on, things to look at before they choose a supervisor or something like that?
Well, in my experience, I'm working with Professor Stephen Julian, and one thing to note is that you can probably take a courses in condensed matter physics. Physics 358 is a good example. And if you're going into your third year, Physics 356, I know it's a hard course, but that is the way that you have to go if you want to do quantum stuff. Yes.
So this is more or less about like the focus of the methods and whatnot. Like I know it's like throughout the experiment you split the procedures, but how did you figure out like potentially any uncertainties or errors with the experiment? Potentially how did you do this yourself?
So basically, the only sources of uncertainty in the methods are from the weighing scale.
Okay.
I went to the uncertainty through those because the weighing scale in the basement of McLennan, it tends to oscillate between a few milligrams. Mm-hmm. So I took note of that uncertainty, but I don't think it really mattered too much.
Really? Okay. That's
Yeah. But going back, I would suggest like if you want to look to finding a professor, maybe just read a little bit and look a little bit into their papers, look into what they do, and just keep applying.
Thank you.
No problem.
All right, you're good to go. You can unplug and exit the meeting. We're off recording, by the way, for anyone knowing, for anyone who's interested. Okay, our next speaker. Looking at my list. Our next speaker is Irmak, and they'll be starting right now.
Yeah.
We'll go here.
Thanks, dog.
You head back to lunch by chance?
Oh shoot! I did not mean to turn that off. I am so sorry.
No worries. Actually,
Dude.
See you around. See you.
do we need it? Oh my gosh. Okay, we will.
Because I think like people
Oh, yes, we do.
and whatnot.
This is a little new to running. Sorry, who is Irmak? Sorry if I'm pronouncing it wrong. How do I say it? Yeah, nice to meet you. I'm Walker on my iPad. No worries. Everything's going. It's just a moment.
Oh, hey. Nice to meet you.
Yes.
And you can just swipe. It's already sort of in meeting, so it should project onto there, and I'm recording it. Is that okay? We could also,
At least for that.
yeah, you don't have to record.
Like
But we were thinking like record your own talk.
Yeah.
If you want to record your live stream talks, or you also have a recording at the end, yeah, let's send that to you. You can also let us know if you want to. We've got it recorded on this.
Oh, okay. They're recording.
I just need, yes, check the remote. Yes. All right, we'll put you up over here. Take this for sure.
No, it's not that.
You don't have to like talk.
It's not that guilty. You already know. Basically, what I'm doing is the right. I add.
Yeah.
It's good. It's good again.
All right. I think
That's not going to work. We're just changing the properties. Yeah. It's like
Julian, do you hope
Yes.
do you hope to stay this on?
It's on. It
It is
should.
on, okay.
When it's beeping, it's just gonna heat up for a moment, and then it should be good.
Okay, got it. Then we should be on in a second, and then we'll resume, and we'll have a break after this talk.
Okay.
Okay, perfect. All right, and I'll let you know when to go. Exactly. Okay, everyone good? All right, so we're going to invite our next speaker. You guys can come have a seat quickly. Just in time. Sorry, you said your name was Irmak? Irmak, okay. So, guys, we're going to get started. Our next speaker, Irmak.
Yes.
Okay, perfect.
So,
Right, take it away.
nanoparticles are almost impossibly small. To give you a sense of scale, a human hair is around 80,000 nanometers wide, and our particles are roughly 8,000 times smaller than that. And yet, what happens at that tiny scale, how the atoms are arranged, where the impurity of the atoms sit, and how many electrons they lost, completely determines whether the material glows, detects radiation, or does nothing at all. My name is Irmak, and I'm a researcher on a project investigating a material called doped calcium fluoride in nanoparticle form. A few weeks ago, my team and I traveled to Brookhaven National Laboratory in New York to run experiments at the National Synchrotron Light Source 2, which is one of the most powerful X-ray facilities in the world. Today, I want to walk you through what we did there, how the synchrotron works, and what we're finding. So before I get into the material, I want to explain one key concept called doping. Doping means deliberately adding a small number of foreign atoms into a crystal. These foreign atoms, called dopants, slot into the crystal in place of the host atoms. And by doing that, they change the material's properties. For example, in semiconductors like silicon, doping controls how the electricity flows. In optical materials, which is what we're working with, the dopants act as high light-emitting centers. They absorb energy and re-emit it as photons. But here's the thing. How that emission behaves depends very sensitively on the local environment around each dopant atom. If you change the bond length or the arrangement of the neighboring atoms, then you change the color intensity and the efficiency of the light emitted. So the central question of our project is, where exactly do the dopants sit inside the nanoparticle, and what does the crystal look like around them? I'd like to explain why we're working with calcium fluoride. Calcium fluoride is a simple ionic crystal, calcium and fluorine in a face-centered cubic structure. What makes it a great host for optical applications comes down to three things, although you can see four things here. First, it has a very wide band gap, about 12 electron volts. That means it's transparent across a huge range of wavelengths, so dopant emission can actually get out. Second, it has low phonon energy. Phonons are vibrations in the crystal lattice. They're simply how heat moves through a solid. When a dopant absorbs energy and tries to emit lights, phonons can steal that energy before it can be emitted as a photon. Low phonon energy means less of that effect happens, so the emission is more efficient. Third, it's chemically stable and can accommodate a wide range of dopants. We're working with hafnium as one of our main dopants. Hafnium doesn't emit light itself, but it has a charge of 4+, while the calcium it replaces is only 2+. That charge mismatch causes structural strain in the crystal. So I edited the slides a little bit, but this is the right slide. And our preliminary electron microscopy work showed that something very interesting. At higher hafnium concentrations, the particles stop being spherical and start forming flat plate shapes. Structurally, we're seeing something unexpected. The hafnium is moving the surface instead of spreading out evenly. To really figure out what's happening at the atomic level, we need data from a synchrotron. Let me go back. So what is a synchrotron? At its core, it's a particle accelerator, but not the kind that smashes particles together. This device is a particle accelerator focused on light generation. It accelerates electrons to near the speed of light in a storage ring. Powerful magnetic fields force these electrons to change direction, causing them to emit synchrotron light. This light is an intense, focused beam of electromagnetic radiation spanning at a vast spectrum, from infrared to hard X-rays. Synchrotron light is used as a powerful probe for state-of-the-art experiments across a lot of fields of science. This studies structure and behavior of materials, molecules, and cells. So what makes this light so special? Firstly, its brightness. The synchrotron beam is about 10 billion times more intense than a conventional lab X-ray source. Second, it's tunable. Using devices called monochromators, you can select almost any X-ray imaging you want with very high precision. And third, the beam is highly collimated, meaning it travels in a very tight, focused line. So, coming to our experiments, you can see here a photo of some of our samples. Our samples were calcium fluoride nanoparticles with varying concentrations of hafnium, from 0.5% all the way up to 100%. We synthesized them back in the lab, dried them, and pressed them into small pellets for the measurements. The technique we used is called X-ray absorption spectroscopy, or XAS. Here's how it works. We tune the X-ray energy through a range that includes what's called an absorption edge, the specific energy at which core electrons inside your target atom get kicked out by the X-ray photon. For hafnium, that's the L3 edge, at about 9,500 electron volts. The spectrum has two regions. Right at the edge, you get the XAS X-ray absorption near edge structure. This tells you the oxidation state of the atom, meaning how many electrons it's lost, and something about its coordination geometry. Further above the edge, you get EXAFS, extended X-ray absorption fine structure, which shows up as oscillations in the absorption signal. Those oscillations come from a quantum interference effect. when the X-ray kicks out a core electron, that electron travels outward as a wave. It bounces off neighboring atoms, and the reflected wave interferes, constructively or destructively, with the outgoing one. The interference pattern is encoded in the absorption spectrum, and by analyzing it, we can extract bond lengths, coordination numbers, and local disorder. Essentially, EXAFS gives us the atomic neighborhood of every hafnium atom in the sample. So each scan takes about 20 to 30 minutes. We average multiple scans per sample to get cleaner data. That's a photo I took at the beamline. So before I get into the data we got from the synchrotron, I'd like to remind you why this matters. Scintillators are materials that convert radiation into visible light, and they are used in medical CT scans, PET scans, CT scanners, PET scans, and security detectors. The better we understand how to engineer these materials at an atomic scale, the more efficient and precise those devices can become. So, early findings. First, XA-NES. Across every sample from 0.5% hafnium all the way to 100%, the edge position stays consistent with hafnium 4+. So hafnium keeps its 4+ charge no matter how much we pack in. It's finding ways to accommodate that extra charge rather than falling apart. Second, there we go. EXAFS. As hafnium concentration goes up, the oscillations in the signal get smaller. Smaller oscillations mean more disorder. The atoms around hafnium are less regularly arranged. This matters because disorder affects how light gets emitted, and the regular crystal field around the doping changes its emission energy and efficiency. So we're currently working on fitting the EXAFS data to model based on the non-fluoride structure of calcium fluoride. Early results suggest that hafnium fluoride bound is slightly shorter than calcium fluoride, which makes sense because hafnium is a smaller ion than calcium, and the number of neighboring around hafnium drops at high Doppler. So in the bigger picture, if we know which concentrations keep hafnium in the bulk versus push it to the surface, we can tune it to synthesize to get the distribution we want for a given application. So we started this research asking a very specific question. And turns out that question matters a lot because the answer determines whether these nanoparticles glow efficiently, whether they're stable under radiation, and whether they could be used in next-gen medical scanners or detectors. Using the synchrotron, we found that the crystal is more resilient than we might have expected, that hafnium's behavior changes dramatically with concentration, and that this change in behavior is what's driving the shape transition we observe in microscopy. The hope is that eventually this kind of atomic level understanding feeds into materials that make medical imaging cheaper, radiation detectors more accurate, or solar energy conversion more efficient. So physics at nanometer scale with real consequences at the human scale. Thank you, and I'm happy to take questions.
Thank you.
No questions. There you go, yeah.
What's something you didn't expect to be doing in this project when you first started?
Actually, funny story. The facility is in Long Island, so it's a little bit further from the city center. And when we arrived there, it was a full-blown snowstorm. So the beam was down, and it's never down. So we went there, the beam scientists can't get there, and it was very uncertain whether we were going to be able to collect the data or not. So the way we operated it was remotely. So the beam scientists told us how to operate the beam from their location, and that's pretty much never done before. So that was pretty challenging to get the training right there, and then to understand how to operate it and to make the scans ourselves was Yeah.
Wow.
That was pretty crazy. I am a computer science student. I'm also studying astrophysics. Yeah, I'm an undergrad. Second year. So I like working with data, cleaning data, and I think physics professors like that because comp sci background gives me like a wider perspective in working with data. So I actually started to just, just get the data and clean it, whatever. But some of the students dropped out of the group, so I had to take more responsibility. And then I visited the facility, and it was pretty interesting. So, yeah.
So how do you find doing these experiments on like big synchrotron sources compared to like running a diffractometer like in the basement lab?
Oh, like visiting like the facility?
Yeah, or like the sort of process of like running it, acquiring data. How does it compare to the smaller scale equipment?
Good question. First of all, the process of getting approved beam time and then going there takes about like 4 to 6 months of paperwork. So it's a lot of like anticipation built during that time because wow, something's great to like about to happen. And inside the facility, it's huge and you're able to interact with a lot of great scientists working on like different experiments, which is not really the case when you're working at like a simpler lab. It's usually isolated for one thing, but since these facilities are like so wide in terms of like opportunity, you can see a lot of different experiments kind of running at the same time, which I think is pretty cool. Yeah.
I think that's all the questions. Thank you very much. All right. We've got one more. I made a mistake. We've got one more speaker and then the break. It's slightly out of order on the schedule. Here. Oh, perfect. Just in time.
Oh, I got lost, bro.
We've got like a minute or two while we set up, and then we'll do the last talk before the break. All right. You want to get plugged in there? I think I don't have your slides, right?
Oh, yeah. Dude, it's so cold outside, bro. Hi, everyone. My talk. Sorry?
Get into it very quickly.
So, no streaming.
I've got you here on the splash screen. It's got no audio, no video. So the stream's still on, but there's nothing on. Right? Yes, it should connect. All right, and then I'll tell you. Oh wait, I guess I don't need to record, so you don't need to enter the Zoom meeting. You can just share. All right, guys, we're about to get started. So if anyone needs to leave, funnel out if you can.
Thank you.
Yeah. We'll be fine. No problem.
Dude, it's so cold outside.
We'll be fine.
It was
I did.
specific topic.
We don't have too much time to talk about it now, but happy to talk about it another time. It's really good. Good to go?
I guess so.
You're technically not supposed to be grounding, but it's still great.
Oh, no, it's just,
After this stuff. Right. Okay. But since we're not streaming, it's slightly more chill. I'm timing. Okay. I want to invite our next speaker, Tomi.
Yeah.
Pronouncing right? Okay. Round of applause.
I'll be sharing how Metasurface can be simulated using finite-difference time domain and how it could be enhanced for first-order efficiency. So the objective is to maximize first-order efficiency in the 210 and 400 nanometer range and suppress the unwanted order, zero order, negative order. I'll be validating the performance using FDTD, which is finite-difference time domain. Make it for fabrication in a nanofabrication laboratory and apply it to cube satellites. I'll explain what those mean in the next slide. So metasurfaces are relatively new in the field. In the 21st century, they started as a metal material which showed potential in controlling light very precisely. And in 2010, we became what we know today, the metasurface, which is, just imagine a very thin material, an engineered material, that has patterns on it, and those patterns are sub-wavelength in size. Meaning if you're operating in a 300 nanometer range, then the structures would be 300 nanometers and less than that, not 300 nanometers. They're good because they can do like precisely and control transverse electric and magnetic independently, which I think is quite remarkable. Are you guys good at transverse electric and magnetic? Yeah? Okay, good. My pattern uses nanopillars. And there's a photo of transverse electric and magnetic. So this is how the grating looks like. I wish I had a better resolution picture, but my laptop can't handle it. So let's see. Oh, so the blue you see is just empty space. The white is silicon oxide, it is the substrate. The red is hafnium oxide, which is 2 nanopillars. One is smaller than the other. The reason why I use hafnium is because it has higher refractive index, which just means that it is able to delay light, and instead of losing ultraviolet into heat, we can use it for metasurface. And the green is magnesium fluoride, which is a coating to prevent the ultraviolet from reflecting away instead of falling into the metasurface. And how the nanopillars control light precisely is shown in that image at the middle. The nanopillars act like an antenna, and since light is a wave, since light is a wave, they'll make the wavelets oscillate with delayed light, and also redirect light. So conventional gradients leave a lot of the power into the augmented order. So the first order, the zeroth order is simply light hitting the surface and reflecting off without diffracting. And you can see the default is 45 degrees here. The higher the order, the positive order, the higher the angle, and the lower the order, it just reflects off at a low angle. Yeah. So I'm just thinking what I'm supposed to say. Oh, metasurfaces, they are very good because they can create destructive wavelengths, meaning any unwanted wavelengths are destructively interfered, so they are basically forced to be cancelled out, and all the wanted wavelengths are kept. That's why they control light very precisely. So finite-difference time domain, has anyone heard of that before? So it's a numerical computations, simulation. Finite-difference means small changes, and time domain is over space-time. So just imagine a light wave going through space-time, and instead of having like a big simulation, it breaks it down into small chunks, step by step. So I guess every frame you could say it solves the equation for it. For our purpose, I'll be using it to simulate how light interacts with materials. I used Python and MEEP, which stands for MIT's Electromagnetic Equation Propagation Library. I use this because it's free, and other software require a lot of, it has a high cost. The only downside of MEEP, well, it's very powerful, but the downside is that you don't get to visualize it. You just get the data table at the end. So I'm operating in 210 to 400 nanometers. And that's it for that side. These are my results. So the far field comparison shows that actually the field far away. So the picture on the very right side is a conventional diffraction grating with a lot of dips and unstable. So a lot of fluid that go missing, well, lost. With a metasurface, which is the ones at the bottom, have a much more stable control. Well, kind of. These are preliminary results. Right now, the focus was transverse magnetic because, as I said earlier, metasurfaces can control light, transverse electric and magnetic independently. So this is the near field results. This shows the electric magnetic field very close up. It reveals how light interacts in one unit cell. So one block for each of those graphs is just one entire complete pattern of the diffraction grating. The graph on the left, the three polarization graphs, they just show, the red ones show how much energy is in certain regions, which have higher potential contributions. And the blue and red one just shows how transverse electric and magnetic interact with each other. The graphs look like sky. It's not the sky, it's just the diffraction grating. The arrows show, well, the straighter the arrows are, the more, it's like more fluid flow, and the swirls, it's like more concentrated energy, it's like kind of delayed or trapped energy. So the limitations of metasurfaces is that they're very hard to fabricate and very hard to design because at mass scale and size, you need very expensive and big machines. The goal is to find a way to fabricate it in a less costly way, so much cheaper, at a small scale. The other limitation is that metasurfaces can only work in a narrow range of wavelengths. Oh, and I don't have experimental work, which will be in the future. Right now, all these are in simulation. Some applications would be in CubeSats. Have you guys heard of CubeSats? Oh, okay, so you know satellites are really big. We could make them like really small, like 10 by 10 by 10 centimeter big, like a cube. But they're very specialized in what they do. And because of the size, there's only so much you can. Like, if you were to put a spectrometer in a cube, have you guys heard of a spectrometer? Oh, okay. So if you want to make a spectrometer, you have very little space and very limited amount of weight you could have. So what the goal of Metasurface is to use a simpler spectrometer and have the Metasurface do more of the work, so you can reduce optical components and therefore reducing the weight. So you could have similar diffraction efficiency with a simpler optical layout. So the spectrometer on the image is a cross-Curly furnace. It consists of two mirrors and one diffraction grating. The diffraction grating is the one that has like blue and yellow light. The one in yellow. Oh, that's all. And that's me holding the rock.
Thank you.
Thank you. Any questions? Yeah.
You said that one of the limitations was there's only a narrow range of wavelengths you can use. Is that for like any particular surface or just in general to make a meta?
In general, in
Surface.
surfaces, because so my device is optimized for 200 nanometers, and it works best at the 300 nanometer wavelength. Other wavelengths, which is the one I'm working at 210 to 400 nanometers, they all interact with the material differently. They don't interact with it as perfectly as if it were in a 300 nanometer range, but since it could delay light and it could also redirect light, it gets very close. Yeah, it gets close, very, very, very close, so you can have it up to like more than 90% efficiency and reduce zero order to almost 8% or less.
And that's in general or just for the wavelength that it's specified for? It's very effective. Like the one that you're studying that you've optimized it for.
In general, that is how Metasurface work, but for my design, yes, it works very well with 300 nanometer. So is that the question?
Yeah.
Yeah, in general, how Metasurfaces work is we work either for one wavelength, and any other wavelengths are interacting with the material differently. So up to a certain point, it could get really close to how it works in a 200 nanometer range. That's why mine is at 200. Yeah, that's why mine is at 210 and 400. You might be wondering, why 210 and not 200? It's because my Metasurface doesn't work below that. And it's very hard to make up to 200, like in the graph, if I can show it again. Actually, I show it again. Sorry about that. You can see how dramatically, pretend this magnetic, you can see how dramatically it drops. Yeah, 200, at the 200, it drops so low that I didn't want to move it. So, and it wasn't important. So, like, for my certain applications, like space literature or space astronomy, 210 didn't matter for my applications. 200. I just cut it out. Yeah, people find it strange why I have that 10 millimeters out, but it was very hard to work with 10 millimeters. I spent like 6 days trying to get it down, it didn't work.
Yeah.
Any other questions about maybe applications or? Well, most people will wonder about the CubeSats because never heard of a satellite that's really cute.
Yeah, I actually did have a question for that. So like theoretically you put different like meta surfaces on different ones, and then like each one can be optimized for like receiving certain wavelengths very efficiently.
Oh, sorry.
Like would you have different meta surfaces on like if you launch like a small group of cubes as opposed to trying to launch one really complicated spectrometer that's very heavy? Would that be the idea, or just because it's a small material, you could just fit a more simple spectrometer but do a material that optimizes the signal?
That's the goal.
Okay.
So one satellite
Doesn't need to be multiple. Yeah.
Doesn't need to be multiple. Actually,
Cool.
Metasurfaces are great because they can manipulate tremendous electric and magnetic independently. So, yeah, you wouldn't need more than one.
Makes sense. Cool.
Okay,
Any other?
questions?
Okay. Round of applause. Well, all right, we're on break. We've got till I had not memorized the schedule. We've got till 5:25.
Oh wow.
That was good.
Oh, really?
Yeah, that was interesting.
You all fall asleep, right?
Oh man, that was actually really interesting. I should have more questions. So like,
Yeah.
what's specific about like, I guess when you say the meta material, is it like, what makes it different from the other surface? This one was like nano engineered, like there's a.
So they're both nano. And that's in materials. They're like, they consider three-dimensional, so they don't need to be flat surface. Metasurface, the only difference is that it is on the surface.
Okay.
We call it two-dimensional because they're not actually two-dimensional, but everything in life is two-dimensional. But we call it two-dimensional because of how flat it is and small. So Metasurface is basically
guess what's special about it that differentiates it from like just the
Different
typical
optical
surface?
different optical components like
Yeah.
prism or prism.
Or I guess like a regular diffraction grating or something.
Regular diffraction. So on the graph I showed a regular diffraction grating like this. So it's unstable. A lot of bits, and a lot of places, like let's say I want to see the whole range, you can't because you have a lot of noise, you have a lot of black spots, you can't see a lot of the
Okay.
results.
Okay, so that makes sense for like why it's useful, but then I guess like structurally it's different. It's just like the geometry of the surface, the way it's made
Oh, I see.
produces that higher efficiency, like makes it so that it gets rid of noise. What is it that makes it like a metasurface?
So the metasurface is unique because the structures itself, they're sub-wavelength in size, meaning the
Okay.
structure are smaller than the wavelength you're working
Okay, that's sick.
That's
So
why
when you work with these really small structures and you very precisely make it like when you allow yourself geometry that's that on that small of a scale, you can get rid of noise.
yes, because light is a wave like this, right?
Yeah.
And those pillars act like an antenna, and those electrons inside. And let's say
This actually is starting to make more sense. I'm a little slow right now,
oh no, that's good.
but when you're sub-wave, like you can manipulate,
yeah,
you can like it's I guess in simple sense like mold the surface to like the wave itself as opposed to just roughly.
it oscillates the electrons and it, like
Oh, okay.
yeah, and
That's
that
so
only works
interesting.
because the structures are the same size or smaller. Otherwise,
That's sick.
you would have like a traditional grating where it hits the structure at an angle. The traditional grating that is best at performing similar to metasurface would be something like magnetic oscillation. I just hits it at an angle and bounces off at an angle. And that isn't as efficient as literally manipulating the light to
Surface to match the light in
Yeah.
a way, and then you can extract all the info you want. And like that makes sense. I mean, like I've got to see the geometry of it, of like why that works to match the wave. But that makes sense in principle. Like you can match them. It's like almost like making the material resonant with the wave,
yeah, exactly.
right? And then you can get all the information. It's anti-resonant with all the other wavelengths, so you get rid of noise.
Yeah, exactly.
Cool.
Wow, you understood it so well.
That made sense as far as they go. Also, the top before you touch, actually, I feel like was like it made sense too. It's pretty approachable. Yeah, you did a good job.
Really?
Yeah, I
Okay.
feel like were you kind of nervous? Super nervous.
My heart was racing. Like I thought you guys could hear my heartbeat. That's how
You
hard
did
it
really
was.
well. You didn't have to be that nervous. I actually thought I feel like the challenge in a lot of the talks is like it's hard to distill info and decide like what you can communicate and what you can't. People will follow, but I feel like you communicated the main points.
Uh-huh.
It's nice.
Okay.
Yeah, good job.
Maybe in the future I'll be complimented to
Well, I don't know that there were many viewers on the stream anyway.
Is there even any?
I'm not checking. I wasn't checking.
Okay.
Right, we'll be back at 5:45 if you guys want to watch any others. We'll have 2 more speakers. These ones are so good.
Okay. One topic first. Alright. Are you in physics too? Oh, I'm on physics now.
Yeah, I can just ask you.
Oh,
Nice.
See you later. Yeah, interesting.
Yo, I would totally ask him about my research. That's interesting stuff. I feel like you were afraid it was going to be like boring.
Yeah.
But it was good.
You are the lectures, right?
Yes. We are just on break now.
Yes.
We'll be back like 5:25. Did you watch any other talks?
I'm thinking about it.
You should definitely do it because then it will be like a point of reference.
Yeah.
See them before. Because like I feel like you did a good job.
Thank you.
Of course. Yo, I would totally shoot you more questions. Like, what was the experience like? Like, it was all you were working all on simulations, right? Because you can't just fabricate these, or like, I guess if it's expensive, you're going to do all the simulation modeling first, and if like a material is promising, then you might look into trying to.
Yeah.
But
So-
they can fabricate these, right? Like,
Yeah.
theoretically, it's just really expensive.
Oh, extremely expensive.
Because I'm like, if they can manufacture like, you know, I don't know, like really hard, but like, chips with that kind of precision. Like I'm sure we have the tools to do that. It's just that is really technical, difficult stuff, right?
It's the same laboratory where you
That's what I was thinking. Okay, yeah, because it's the same with the chips, right? Like to fit like billions of transistors on a tiny thing. It's nano fabrication.
Exactly.
And is your thing, like, is what you're working on, I don't know like categories too well, but like I was looking, there were like a few profs doing like nanomaterials. Does it fall in that category?
Yes,
okay. Okay, so that's one of the promising things in nanomaterials. That, was that like all of them are like metasurfaces? That's the thing.
Yep.
All of them. Okay.
Yeah.
Cool.
Surface fall underneath that.
All right, cool. I was looking at that. There was I think a younger prof doing that with a research project.
It's quite new, actually.
It's interesting stuff.
Like, actually, we're older than metasurfaces.
Sorry.
We are older than metasurfaces. Like, if you
Oh my gosh! Wow.
Because metasurfaces were first emerging in the 2010, but metamaterials. Okay, metamaterials are older than us.
Older. Okay.
But metasurfaces are relatively new. Like 2010, and metamaterials is like early 2000s.
And is metamaterials, I guess, the same principle? Just it's not like
It's not
very thin surfaces. Yeah. Okay. It's like just a material that's engineered with more specific
actually,
properties.
I'm not too sure what metamaterials are. I just know that they are related.
I feel like the talk just before you, hers should be recorded if you check it out. I think she was talking about that, like doping, and they were manipulating the material, and they found precisely how you can manipulate the concentration, how it behaves in the material, and then the properties change, which is really fascinating too.
Oh, okay.
That was, I mean, you can totally, I'm pretty sure I have her slides. Here, if you want to take a look. Yeah, this was her slides.
Dang, her slides look so much better than mine.
You could have used not white, but it was good. If you want to look.
Damn. She looks so
I know, they were good looking slides, that's fair.
Whoa.
But yeah, conceptually, similar stuff, right? Different kind of material though, right? Like if you're there manipulating the chemical structure more, I guess you'd be doing the same, right?
Okay, so she has hafnium as well. She uses hafnium. Yeah, hafnium is a good material because it has a high refractive index. I don't know what she's doing, but maybe she's looking for that refractive index as well.
I think there is a summary at the end.
Oh, what's that? Yeah,
This is what
there
they
you
were
go.
talking about.
Yep.
And then the geometric structure where it's distributed in the material changes, so it
Yep.
creates new properties. That's fascinating, actually.
I didn't know metamaterials are that. I mean, what's it called? Hafnium was that popular. Because hafnium, instead of losing energy to like heat, it keeps like it can bend it and delay light.
Yeah. Okay, and that's also why they ran an experiment. They got beam time in like the synchrotron. It's okay, I read it. I think this is the
Oh, I
copy.
didn't. I just like couldn't, I guess.
Oh yeah.
But we can. Yeah, there's nothing. Okay.
Yeah,
just
you're
just
good.
worried I changed something.
No, you're good. I think they got beam time at the Brookhaven National Lab, and then they tested.
Oh, you got to test it.
Yeah, they did get to test it. I don't know that like if it's half like due to the group, maybe her group was further along and she hopped on the experiment or something. But in the slide, I guess these were the. Okay, yeah, as they alter the concentration, right?
Yeah. How long is it? Until 5.
Yeah.
525. Let me just check. One person pulled out, so I can give you an exact answer. I know, we just borrowed it. It's so much better than our usual one. Yeah, 525. No problem.
Is this one usually open?
I actually don't totally know what this. I think it's a grad lab. I think it's just a little bit on the floor. Every floor has a meeting room, right?
Okay.
Yes.
But yeah, we usually do the talks here in the weekly colloquium.
Oh, you guys did the weekly colloquium?
We do the weekly colloquium. And then this conference, which is like a bunch more work.
How many people attend the colloquium?
It totally depends.
Yeah.
Week to week.
I was like, hold on, why is it moving?
Week to week it changes, but sometimes there's a lot of people. Yeah. It's definitely kind of cool. We just do the recording.
Oh, you know the title I made? Like the first slide where it says the
Yeah.
That was a software that
shows you the design of your nanoscale.
Wow.
That's what you submit to the nanofabrication auditor, and that's what they review.
Wow.
If it's possible to.
What does it look like price-wise? I'm just kind of curious. If you wanted like one sample, like I guess the sample can be super tiny, right?
Yes.
But maybe you want it to be a little larger in case it gets damaged or deteriorates during the experiment, and you want other sections, right? Or something like that.
So an hour on one of those machines, academic use would be like $140 an hour to do one entire task. So.
And how long would it take for one of those, for one of yours, I guess? Like fabricate some amount of that metamaterial. Metasurface.
I'd say a safe bet would be 5 hours. So we're doing one entire, like, just making like lines like this would be like 100 something, almost $1,000. So
Okay.
like.
They gotta give you the budget for that. This sounds interesting enough.
Yeah, they waive it. They waive it if it was a research purpose. They waive the price. No, they give you the academic price.
Okay.
Or waive it.
Cool.
If it's your own university, they waive it. You should see the industry price. They're like
Nice.
500 per hour.
Did you look into? Is it realistic for your project to eventually test it, or like your results aren't exactly where you want them to be, and like you need to push it a
Oh
little
yeah,
more
you're
in
right.
the simulation? Because I know, were you saying that a little bit earlier? Like you got some of your results
Yeah.
like before your talk, but you didn't get everything you wanted, and you're like, I'm happy.
Yeah.
Which like happens. What are you gonna
First, I want to finish optimizing transistor schematic, how I optimize transistor selection, and then from there, I want to keep the result while seeing what I could bring down, like in terms of design and structure to make it cheaper and easier to fabricate. Actually, there's an aerospace team that does small sats, like small satellites. I was on the
Oh,
team,
wow.
and
Okay,
we
cool.
were thinking about using a nanofabrication lab. Maybe, but it's not for a Metasurface, it's for like a slit.
Okay. But same kind of purpose, it would be small enough that you need that kind of lab.
Yeah, we do need, yeah.
Cool stuff.
Because it's very specified, it's not sold. If I were to buy it from somebody else, they
People don't
might
have the
rip it
quality equipment to make this.
off. And they'll rip it and they'll rip us off. So,
Okay.
because they'll price it like crazy. When we could fabricate our own.
And what year are you in?
Oh, I'm in the old age of third year.
Third year. Okay, I'm third year as well.
Oh,
Damn,
really?
dude, you're working on way more stuff. That's interesting. Yeah. Yo, could I shoot you like an email or something to ask if
Sure.
I've got more questions there?
Do you have LinkedIn?
Sorry.
Do you have LinkedIn?
LinkedIn?
Yeah.
Yeah, for sure.
Emails I tend to get very Alright, just like how Pekka said. I mean, Mr.
Yeah.
I mean, Professor Pekka.
yeah. True.
And just across the whole.
Dude, how do people add each other on LinkedIn? Okay, I pull up your name.
Yeah, I just searched my name.
I've never I feel like I've never added someone on LinkedIn like in person.
You know, I went to the small sat
Alright.
conference.
What's your name?
TOMI.
Yeah.
Space WENG.
Angie?
Yeah, that's me. It should be me holding something.
It's like in the wrong. It always somehow brings me to searching jobs.
Oh, my network. You have to go. Yeah, my
Yeah,
network.
this one should work.
Okay. Like midterm.
Oh, there you go. That's me, the first one.
No, it should go. Oh.
You use Google for LinkedIn?
I don't use it enough.
Oh, you can't.
I should.
As a regular member?
Let me check. No.
Oh, okay. I need to fix that.
Okay, good to know. Shit, man, I should check that. I think it's sent.
Oh, it's sent? Okay,
Right.
my phone
I'm
died.
down. Nice to meet you.
Oh, nice to meet you too.
By the way, yo, you sure you don't want the lotion that you got? I barely use this.
No, it's
Dude,
okay.
use it if you're like.
No, my hands, like, I need a very specific one.
Okay, you sure? Take a look.
Yeah, I have to.
It's like alright. It's like a.
Oh,
honey
Bush
one.
Bees now, it's fine. But it's okay, it's okay.
It's Bro, your hands are like cracking, man.
I'll just like,
Are you sure?
yeah. I'll
Bro,
just,
I don't
No,
care.
no.
Dude, I
It's
swear I
okay.
bought this like 2 years ago.
Oh, no,
My
that's
hands were
not-
cracking in the winter, and then like I actually haven't used it this entire year. So it's just been like.
Oh, I just like to, I like to put like something else on it first beforehand, and then wash it. Otherwise, it doesn't like. I have a very
Worries.
extensive skincare routine that I don't follow. But
I
I do it on my face.
I had a
sometimes.
friend growing up who. Oh shit! I'm supposed to turn this on. No, I'm good. I had a friend growing up who needed like a medical. No, we're not. We're on no audio, no video or anything. Basically, like you have all these like.
Hi everyone. Oh yeah,
Sick.
we're already.
You've got all these scenes.
Oh, how many people we got?
We're right now on Splash, so there's nothing.
Oh.
Let me check. We may not have. People might watch the recording after. Oh, we got 3. All right, cool. Sick. All right, let me. I'm totally unprepared.
I have no idea, but Andrew said he heard something. I agree with this, but I don't know what
Super. All right.
Hallie?
Yeah, yo, I'll definitely shoot you a message. It's one of the things I was interested in. I feel like nanomaterials is like kind of one of the more interesting ones to me, in terms of like material science.
Yeah.
It's pretty cool.
Are you interested in material science?
Yeah.
Oh, you are?
So yeah, I feel like I saw a few topics that are interesting, but I didn't like look much into it.
You know
But I have
Iron Man? Like Iron Man makes nano stuff?
Oh, really? Like in the
Like in
movies?
the movie, yeah. Iron Man.
I didn't notice that.
Oh, do you watch Marvel?
Not much. I've seen the movies though, but maybe I didn't notice that he was making nanomaterials.
Oh, he's like he's.
Oh my
super
god, they
nano.
say that stuff all the time.
I
Okay,
know, right?
fair. I wasn't paying attention. They probably say nanomaterial all the time, like as a flashy word. but-
Nanotechnology, yeah.
Okay.
They use all the flashy words like
Yeah. That's why I'm like, I didn't value.
astrophysicist, nuclear astrophysics engineer.
Yeah.
I'm like, what the? That's just a nuclear engineer.
All right. Well, see you, man. Yeah, if you stay for the talks. Lyssa? Okay. All right. I'm gonna. Do you mind? I'll pop your slides open here on the iPad. Actually, you know what? We have a break after you anyway, because one speaker had something come up. So, do you want to do it on your computer?
Wait, like a break after me or before?
After you.
Oh.
Yeah.
Wait, do I have to?
Yeah, just after you.
Yeah. Okay.
Oh yes, you can go a little. Yeah, you don't have to worry about time. So yeah, do you want to do it on your end? I can also put it on my iPad right here. It's easy too.
Yeah, I don't know.
Sure. Okay. Then let me get your slides. Okay.
We actually have to work on a project.
Right. See you, man. Yeah, it was nice meeting you. All right. Yo, I'll shoot your message.
Yeah, see you later.
Bye, dude.
It's so hard to do.
So we came to support you. No, it's fine. I'll let you.
Okay. Is there any way you could send the slides again? They're like weirdly marked as a Google Doc, even though they're Google
So
Slides.
weird, yeah.
Thing. I don't know why. The link is like Google Docs.
Yeah, that's.
And then you can click this on. It's for sure. And yeah, you don't have to talk too much into it. Push the top. Exactly. And you can use the pointer to point if you need. Nice. We don't have a laser pointer yet.
No, I'm very happy with that. Yeah, so just with Khush.
You're doing it back. See, it's so weird.
Oh, yeah, of course.
Yeah. Worst case, we could do it can be and then I will just you're so lucky on this show. Like, I've never seen that before. It's like off slides, the upper box is gone.
Oh my god, now this is on.
Right, where?
That should be a 1/3.
It's Diffraction.
It's fake.
Yeah, I'm
Like
just gonna try out.
there's one. Even presentation. Okay, no.
It's not letting me the power rate. Do you want to do that? Is it okay?
Yeah.
You're good for battery and stuff?
Oh,
Sure.
yeah, I can help put it on.
Do you have an HDMI port there? Since we've got some time after, it's a long rush anyway. Right? And then I'll just get you into a Zoom meeting basically, and we'll have you share screen, and that should be it.
Why did the family
The password is study.
Yeah.
No, the microphone.
Yeah.
Exactly. Then you just screen share. Yep, and I think you're in there. No worries, there's no rush. Guys, we had a change in schedule, so the next speaker won't be able to attend, so we've got like a little bit more leniency in the time. We'll just have another break before the last speaker at 6:10. Okay? We'll get started in like the next 2 minutes. All right, yes, looks like it's working. Right, and then if you can hit slideshow or present. And let me make sure. All right, one more second. This thing like passionately changes the settings every time there's a different screen. Yeah, whatever you prefer. Right. Okay. Okay, I think we should be good to go. All right, we're ready to get started. Okay, so please welcome our next speaker, Lyssa. Round of applause.
Welcome. Alrighty. Okay. Alright. Hi everyone. So my talk today is going to be on the search for dark matter, machine learning in the SuperCDMS experiment. We'll just go ahead and get started. Great. So what we're going to be talking about today, we're going to start out with an overview of the experiment, and then go on to the detector design, which is really important for the machine learning that we're going to be doing today, or I've already done. Next, speaking of, we'll look at the simulation and the machine learning, and then we'll look at validation and reconstruction results, and then we'll conclude in some way or another. So what is dark matter? So dark matter is the solution to a variety of astronomical problems. There's ample evidence to suggest it exists. A promising candidate is the weakly interacting massive particle, the WIMP, which is a really funny name, I know. So a fun thing about WIMPs is that we know that they don't interact strongly or with the electroweak force, but they do interact gravitationally. So a really fun thing about detecting a WIMP particle via SuperCDMS or any other sort of direct detection is that we can enable the discovery of a new fundamental force, which I think is really exciting. I think we should all think is really exciting. And then this plot on the right, it just shows the composition of mass in our universe. You can see the dark matter makes up about 26.6%, which is not a small margin at all. So the SuperCDMS experiment is located about 2 kilometers underground, which you can see in this image here, at Snow Lab in Sudbury, Ontario. This is Snow Lab. It's a pretty big experimental site. SuperCDMS is only just in this little tiny corner here. SuperCDMS is the successor to previous CDMS experiments. I should also expand. SuperCDMS stands for Super Cryogenic Dark Matter Search. The experimental design looks like this. These devices over here are for cooling, hence the cryogenic. We have some shielding and a cryostat to keep cool. Our detectors, which are housed in this little part here. So the SuperCDMS detectors are the bread and butter of the whole experiment. What are they? They're cylindrical crystals made of either germanium or silicon. They're 100 millimeters in diameter, 33 millimeters in thickness being in the Z direction here. The way they work, the way a detection would occur, if a WIMP were to interact with a target nuclei in the crystal, you would expect to see an electron-hole pair coming up in this way and this way from the collision, as well as the production of some phonons, which are amplified by a bias voltage applied to the detector. And the way the phonons will propagate is up and down through the detector, and they'll be picked up by sensors at the top and bottom. So aside from the material, there are 2 types of detectors. There's the interleaved Z-dependent ionization and phonon detector, IZIP, and the high voltage detector, also known as HV. So the IZIP detectors are equipped with both ionization and phonon sensors to be able to discriminate between the nuclear recoils of WIMPs that we're actually interested in seeing and the electron recoils of background events that we don't really care about. Because of this, though, the IZIP detectors are equipped with a lower bias voltage, so their phonon amplification is less than, say, the high voltage detector, which we'll get into in a minute. So they're less sensitive to really low mass scales. Still, they can go down. They're sensitive to masses about on the 3 GeV scale. Now, the high voltage detectors, which I mentioned just now, have a higher voltage, bias voltage applied, about 100 volts. So the phonons that are produced from the collision are really well amplified, so they have a very excellent phonon sensor resolution. And they're very sensitive. They're sensitive to masses down to around the EV scale, which makes them really excellent for detecting very lighter dark matter masses. The diagrams on our right are the phonon channel layout. The phonon channels are these colored patches here. We have phonon channels to be able to reconstruct position information from the energy depositions in the crystals. Each detector has 12 phonon channels in total, with 6 on each side, and we'll get into those more on the next slide. So this is a close-up of the HV detector phonon channel layout. The HV detector are the ones that we're going to be looking at in this presentation, just because of their higher phonon resolution. So this is really complicated. There's a lot going on in this diagram, but the features of interest are the phonon channel names. So the phonon channel naming convention is P star S1 and P star S2 for side 1 and side 2. Star runs from A, which is the outermost channel, all the way into F, which is the innermost channel. Something interesting to note is that the way we reconstruct X and Y position is through these wedge channels, channels C, E, and D. Otherwise, the radial reconstruction is pretty intrinsic to just the geometry of the crystal, as well, in addition, like the azimuthal component is pretty intrinsic just to the geometry of the crystal. Right. So let's talk about machine learning and simulation. So first, why am I talking about simulation? Why not just train my machine learning model on regular old data? Well, it's complicated. So the motivation to use simulation samples to train models are mostly because they're easier to generate than just taking data, and they're easier to tweak. So if we generate a sample and we train it and we notice stuff that we don't really want to see, we notice some errors that are really unphysical, it's really easy to go back into the simulation and tweak variables and tweak the simulation to make it more physical and make it train a bit better than it would be to go back in and tweak a regular old experiment. Just to get naming convention out of the way, the detection samples, data samples that I'll be using in this talk are from the Detector Monte Carlo simulator, DMC. I'll be referring to it as a DMC data. It's not really data, it's simulation samples, but not to be pedantic. All right, on to machine learning. So machine learning is really common in all of high energy physics. This is a really, really simplified training flowchart for how we're going to be training our machine learning model in this in all my subsequent results. So we start out by choosing some model, we set some optimization to it, and we feed it in some observables. In the case of this example training flowchart, it's OF amps and OF delay. OF amps are the energy amplitudes measured in each of the individual channels. If you remember, our naming convention is P star whatever. It'd be P star OF amps is the individual channel amplitudes. OF delay is just a timing delay from the top and bottom of the detector from where they're measured. We feed those into the model, and we can reconstruct various parameters of interest. In this example, again, we're reconstructing X, Y, Z, and energy. So for the following slides, you'll see I'm going to be using a histogram-boosted, histogram gradient-boosted regressor, or HGBR, and kind of wordy, kind of complicated. Essentially, a gradient-boosted regressor is a sequence of decision trees with each, it's an ensemble model that's a sequence of decision trees with each decision tree improving upon the errors of the previous decision tree. I'm not going to get any more into that because it's very complicated. The training will be only done on the OF amps, not the delays, because the delay is most important when you're reconstructing for Z. We will be reconstructing for X, Y, Z, and energy, or I'll be. You won't see any of it, because the only parameter we're going to be really looking at is the radial distribution. So, before I go on to the next slide, I should clarify. There are many steps to seeing if our model is trained correctly. The first one to do is validate. So what we'll do is we'll take 80%, given a DMC sample, we'll take 80% of that data and we'll use it to train our model, and then we'll test it against the last 20% of our sample. And we can see the result of that here. So, what does this mean? On the left is the validation plot of true R, this is our 20%, and predicted R, which is our 80% that we've just trained on. On the x-axis, we have reconstructed R. This is a histogram, so it's events on the y-axis. And this is really promising, actually. First of all, they match almost perfectly, as you can see looking at the residuals. The residuals have a standard deviation. Oh, you can't even see. The residuals have a standard deviation of about 0.3 millimeters, which is really good. It means our model is accurate and is predicting things well. And then looking back to this, looking to the behavior, we expect to see that we want to see that the radial distribution is approximately linear. And this is exactly linear, right? And we also want it to be smooth. There shouldn't be any discontinuities in events. So this is really good, and this is really promising. But that's just our model, and what good is a model if you don't have real data to reconstruct? So next, we're going to look at some real data using reconstructed by this model, and see what we get. So this is really wrong. Awesome. But why is this wrong? So I guess we're calling back to the previous slide. We want to see something that goes from 0 to 50 millimeters. If you remember, the radius of the detector is 50 millimeters. The diameter is 100. So we would expect to see a distribution that spans from 0 to 50. We don't see that. That's first of all. Second of all, clearly this isn't linear. And third of all, this does not look like a very smooth distribution. In fact, we can see a really large peak at large R, which is a bit bizarre. And we see that it only goes down to about 17 millimeters and only goes up to about 43 millimeters. So, like I said, clearly something is wrong here. But you can't really do a lot with this plot alone. This doesn't really tell you anything except something is going very, very wrong. So what we'll do to investigate this is look at these plots. And these are a bit mysterious on the face of it. So if you recall previously, I mentioned that the P star OF, or the P star amps, are the phonon channel energies measured in each individual channel. So what this plot is looking at the correlation between the outermost channel, which is PA, the energy measured in the outermost channel, and the energy measured in the innermost channel, and looking at what behavior happens when one is at one extreme versus the other. So what do we see here? Let's look at the DMC data. So we're seeing that when there isn't much energy measured in the outermost channel, for DMC, nearly all of the energy is measured out here in the innermost channel, F. And then vice versa, when there's very little energy measured in the innermost channel, F, all of the energy is measured out here in the outermost channel, A. We don't see quite this extreme a distribution for the Q data. And I guess the reason for this is that even when, for real Q data, when most of the energy is in the, say for instance, the innermost channel F, we see that there's still going to be some amount of energy shared in the other channels, and most notably the outermost channel A. And then same thing, when most of the energy is sort of measured in A, there's going to be some energy sharing still in the innermost channel, because otherwise you would see this very large distribution here. So, I guess to recap that, because that was a lot of words, basically the result of this plot means that there's more energy sharing occurring between phonon channels in the real data than there is in simulation. So how do we fix that? A fix that we've tried is to scale each of the phonon channel energies by 3 parameters A, B, and C, and summing them using sums of the total energy to conserve energy. I'm not going to get into this because it's a little bit complicated and annoying. But basically, applying this to our simulation data, we get pretty promising results, at least for the PA versus PF correlation. Right? We see that now they're like basically on top of each other, whereas before there was not only this space, but Q was way smaller than the DMC. And now, like I said, they're basically on top of each other. Of course, note that this sky is a little fuzzier than the Q data because there just are more events. That's not really a concern I have. I suppose the only thing of maybe note is that still we see the DMC data does have a little bit of a tail out here that the Q data doesn't. But regardless, it's progress. And so now let's apply that to our radial reconstruction and see what we get and see if it's something that we can use. Oh, sorry. So this is just our validation again for now after we've scaled all the energies. Same thing as before, the model is working as expected, which is good. All right. So here is our reconstructed Q after we've scaled the energy. This still isn't great. It's still not perfect. It's still not really that smooth. I think if you squint, you can kind of imagine that this could be linear, plausibly, which is better than before, since before, I mean, it wasn't even at all linear. But then looking to sort of the distribution, how far out does it go, and how previously, remember, this only went down to about 17 millimeters. Now it's going down to like maybe about 7 millimeters. That's improvement. Even better, it seems like the distribution is going out all the way to 50 millimeters, or just about 50 millimeters, which is great. Still, we see this peak at really large R, so that's something to investigate. But regardless, that's promising. That shows that the energy scaling could be in the right direction, and that the energy sharing of the phonon channels was indeed a reason why it was training so poorly. Okay. Like I said, we'll conclude something. So I guess to conclude, as I said, machine learning, as is in many high-energy physics experiments, is needed to reconstruct position data, particle interactions. Energy sharing between phonon channels, like I just said in the previous slide, seems to have a pretty large impact on how well we're able to reconstruct data. And the energy rescaling function shows promise. It still has a lot of work to do, which we'll cover in next steps. So next steps, I guess, on a very basic level, is to investigate the peaking events at large R, see if these are caused by background events detected at the surface, which is a more likely place for background events to occur, and then continue investigating the energy scaling function and see what more we can do to improve that. And that, I believe, concludes my talk. All right, are there any questions? Yeah?
Yeah.
You can be the worst.
Okay. So, I'll do less basic one, I guess. So, if you go back to the slide where you showed the better comparison of the DMC.
This guy?
What is this little line thing you see? It's very faint.
This guy?
Yeah, linear piece. Does that mean anything? Is that
So, actually, I do have a really good answer for this, and it's, this will take me a second to explain. Basically, this is a bit of an oversight on my part. What I did when I retrained this, okay, hold on, how do I explain this? So we can train on specific like energy, like cuts of energy, because basically when a phonon collision occurs, there's like a whole spectrum of energy that we can look at, or we can also look at just cuts of energy. Previously, I was training and then testing on just one cut, which we call the K peak, due to like characteristic X-rays that I'm not going to get into. Which is why before there was like far less. It was like far less fuzzy before, if you remember. This time around, when I apply the energy scaling, I also trained on the full data, the full energy spectrum, because we found these energy scaling parameters from the full energy spectrum, and it doesn't make as much sense to just train on the one small section of energy that we had before. If sort of the scaling parameters that you're using are like kind of derived from using the whole energy spectrum. If that kind of makes sense. So what you're looking at is the comparison of the CaF data. This is just the K peak of the CaF data versus the DMC data, which is the whole energy spectrum. So to be honest, the fact that it does look this good is like kind of a miracle, considering that like I'm kind of comparing apples to oranges, and that's a bit of an oversight on my part. I didn't have time to fix it. But yeah, sorry, it doesn't really mean anything. Also, there is a bit of nonlinearity. I believe in this factor, something in the inner channel to being a bit fuzzy. There are some events, like events of these guys that I think go down, like way down to the negative, which is impossible. You can't have negative energy. And that's an issue that we still have to fix, I believe, in the simulation. So that's actually a really good question. Thank you. Any more questions?
Why do you care about the papers being
So, I'm so glad you asked that. I'll go back to this slide. So I mentioned when phonons are produced by this collision, they're sent up and down to be picked up by sensors here. But I didn't really talk about what the sensors are, because it's a bit superfluous information. But the sensors are, they're kind of two parts, and they're a bit complicated. But very basically, the first part of the sensor happens when the phonons reach the top and bottom of the crystal. They get absorbed into superconducting aluminum. This is why we want our detector to be cryogenically cooled, because I still think we don't have room temperature conductors. So basically, when the phonon is absorbed into the aluminum is superconducting because it has Cooper pairs in it, which are electron-electron pairs. And the phonon is absorbed, it breaks the Cooper pairs and generates quasi-particles that are then absorbed into these, I believe, superconducting tungsten. The absorption of the quasi-particles heats up the tungsten, which changes its electrical resistance. And then the energy needed to bring the electrical resistance back to its nominal electrical resistance can be used as a calibration for the energy deposited in the crystal. I'm sorry if that was a bit wordy, but it is a very complicated system. Any more questions?
I think that's all for today. Thank you very much. Yeah, you're good. You're off recording too. All right, we are on break till 6:10. So yeah, feel free to grab cookies, juice, and we'll have our next speaker then. There's juice. I don't know. I think it's juice.
Oh my God, please ask them. I love it.
Listen, I'm so sorry about the bottle. I was really drunk.
Sorry, what?
I didn't even notice that.
I didn't even hear. Okay, so I asked questions that range from like why the hell do you hate that? So one very basic.
Really, this is a blast sitting here, like listening to all these talks.
So
Yeah, kind of fun.
Yeah, like I mean, it's gotta be a bit stressful, like I'll bring that, but like once you get the hang of it, it just seems like, kind of chill.
Yeah, it's not too bad. It's always like the first 2-3 minutes that are kind of stressful because you got all these little like adjustments.
And you're
But
under a time crunch as well, so.
yeah, like I felt it's got like little annoyances. Like literally every time I have someone screen share on Zoom, like once it's a Google slide, once it's a PowerPoint, even 2 times it was PowerPoint. Somehow all of the things are out of scan, and then you need to recrop them.
I need to send you my news.
Oh, sorry, the last speaker.
I made a bunch of changes.
Khush. Hey, wait, I feel like I've seen you talk about you like last year. Did you do one too? I don't know. Or earlier this year.
It was,
Sorry.
it was a couple weeks ago.
Okay, a couple weeks ago. Was I there? Okay, why am I forgetting whether I was there? Okay, maybe I just saw your name in the thing. Okay. Yeah, sure. Feel free. Do you have access to the Discord? Also, I can get it on my iPad. We don't really need it. It was a little bit better when there was like multiple speakers in a row to try to get them. If you want, you can definitely just. I can just plug you in.
Okay, yeah. I think that would be just easier.
It was more like that was an advantage when there's many people in a row, so you don't all have to keep plugging in to get it on one computer.
That makes sense.
The interruption kind of means it's not needed. So yeah, and then I'll just have you enter a Zoom meeting and share screen basically. And I can give you the ID and password as soon as you're good.
I mean, I still have like a couple of
Sure. I'll like 6:05. I'll get you in the meeting, but you can still edit things all the way. You can edit during the presentation.
Let's say, maybe you like land Right. So there's photons are like vibration effects. But that's like this is like energy. It's really small. And the energy is like you're gonna use frequency, right? But it's not going to just like this, right? I mean, because it's like independent here, and like obviously it's very visible in this channel. But like there's going to be some energy shared. Oh, I should specify actually. One of the parties of the energy shared is something called Analytical.
You can sit here. I'm just gonna use this chair to help process over it.
Oh, perfect. Okay, so basically what that is
Back to your head.
and it scatters off at some angle. But now, because of the scattering, it has reduced energy, which we're down to with anharmonic. And that has something to do with you're not going to get this in the alpha intended, but this effect causes the whole crystal to have kind of a phonon soup going on. This phonon energy is like dispersed, like a soup, some of these flood gas, among all the photons. And I call it super. Yeah.
Was it freezing outside, but like so hot in here?
March in Burn Tower.
Oh my god. It's like, how can you be the worst thing at both times? Indoor and outdoor both suck for the opposite reasons. It's still open.
They're talking to me.
It's, physics students, sad people, I see it.
I like to study with my friend on this before office a lot.
Yeah.
It's a nice place, it's usually empty. Like, around this time of year, it's just awful. And we can't open the windows, we can't do anything.
Yeah.
And they still to get work. Like,
Dude, I feel like spring and fall are worst. Because you're back and forth and you haven't switched everything over.
you would have thought people knew how like HVAC works in the 60s.
I know. It blows me away. Also, the irony of doing, like, you know, there's like cryogenic refrigerators here, and like you can't get the freaking AC working. Well, I guess they just don't have the money.
Yeah.
They have the theory.
It's at least a little better in Europe, where it's like you're allowed to use AC for these furnaces. You're not really allowed to use it for the heat.
Fair enough.
I hear we're allowed to. You just can't make it. You know?
It doesn't work well. Bureaucratically efficient.
Yeah. Do you use latex?
Yeah, I mean, that's how I got these.
Yeah, but couldn't you type in the latex in there? There's a movie.
Yeah, I could, but I don't like the
I get what you're saying.
But like, how'd it go? Sorry, how'd the recording go? Good?
No, it's
Okay, nice. It's fun here.
It's funny, it's so noted. I feel like that is safe to say that's beyond the scope of this. Like, yeah. I don't know. I do want to understand it a little better because like there's my views everywhere. Sorry. Could we plan more questions? I do. So you get more for no, please ask. So why do you think about 80% of your model is not good? Oh, okay. Like, are you asking like why does it? Yeah. I don't know, to be honest.
So did you guys
That's
upload the
sort of like when
recording?
people bring a lot of Facebook
It's on your computer, right? You're running it? Okay.
I
Okay, cool.
assume that that's
Does it automatically save live streams? Am I trolling? I think it saved live stream.
I want to say it.
Yes, okay, sorry, that was for when we couldn't get the live stream working. Okay, never mind. Should be good.
Right, that makes for a better like model. But then I also want to have
Yeah.
some amount of data left over that you can like test on, like that's something actually substantive on like testing out. And I feel like each one feels like a different split. But yeah, that's about
You're right. So the size of the dog implies the size of
The
the
last one
dog.
that like has enough detail to be answered and that isn't like is so like obviously knowing the real value of the noise. You found that anywhere like simulating something? So that's actually a really interesting question.
When you move HTML,
Because our whole thing, the whole thing
it's probably like
is
marginally better.
and there's a lot of work that goes into
I think the last one
that
that we
we
did
actually have something called finalization cut. Which like basically what you're looking at that I just constructed, we've already cut out like
Let's say it works.
I think it's been like 6.9% of like background has
You can also unplug if you want.
we've already the data from Johnson already cut out so many events. Still, actually, hold on. I'm trying to think. I think a couple of meetings ago we actually mentioned we were talking about
That
that
is very odd. You want to present on
If
another
I
tab.
remember
I
correctly,
don't.
we expected that around
Is this like your presentation?
3 to 5.
No, that is mine.
It's actually kind of
Okay,
small
yeah.
considering how big that is.
I guess it prioritizes that.
How much larger than the regular, or like how high it is. It can have
It's not working. I can't add the double dash.
I'm just laughing because they're doing that.
I mean,
so for a moment I'm like, you could like try to make iced tea. It'll take like 1 hour to brew in cold water or something.
See the window, but you just like put your cup there, and kind of collect it. Maybe like take off your glass.
Or just keep holding it with your hand. Yeah, there we go. Analog boiling.
So I can't exactly remember what one. This is an Instagram actual, and this guy should I think have more events in general than this guy. But I mean just you can just compare like this goes 5 times. Oh shit, this one goes 5 times. Yeah, but I think even just like comparing like what's the nearest guy, like this guy has a computer. But if you look like let's like look at 30, and it's like this is like 3, so it's like versus this guy, this is like 300. You go to 30, it's like
Yeah.
yeah, it's very
Because if you just got rid of this P, this part.
Guys, there's also water if people want. There's a water fountain.
I can just tell that we think the same way because as soon as you switched this, I was like, oh, it should switch now.
6:10. Yeah, we got another 10 minutes.
This thing, like, ignore that. Like, if you just look at the things that are there, it's like,
I mean, when you saw, like, when Pekka like, saw this. No, actually, when Pekka saw this, do you remember, like, the first he emailed back, he's like, and he's like, vibes. It's exciting. Because like this is actually kind of exciting. Sorry. No, it is exciting. Yeah. It's exciting for my work. No, but it's exciting because I get to keep investigating this summer. I learned so much. Well, really good talk. You explained every schematic very well.
How's everything going rest of the conference? Good? Cool. Yeah. CaF still has the PhySU key, right? Okay, so I'm gonna...
I do not have my key. I will not be getting it. I'll get it back.
You're like, I don't miss it.
That's responsibility for me.
And if it gets lost, then...
Oh no, then it's
Okay,
all.
then it's fine.
Because Jordan doesn't help.
True. Alright.
No, but Emily had my
Alright, we'll drop off this equipment in we'll lock it in the office because they're closed, and then on Monday I can grab it sometime in the morning.
Well, I can also try and bring it.
It's so good. You can. I took it from. It's from 125. We borrowed it. Basically, it's so good. Like if you look, not only does it like autofocus when you move, you can like save multiple zooms. So like this one's on the front, and then like this one zooms into their head for when I go back. I know, and it's really good. And then it keeps refocusing. Exactly. Yeah. Now the one thing I think I somehow keep mounting this backwards because when I want to go left, I get it right. I didn't figure it out. It didn't work. I moved it around and it still didn't work. It's like okay.
We should absolutely borrow these. Here's how. I should tell
Could be
you.
inverted like that
We
because of
should
the
borrow
camera.
these for
Sorry.
Could be inverted like that because of the camera.
good
It
camera.
could be.
Because you know how like it's like where you're not cameras like technically.
You're right.
Whatnot.
Wait,
Sounds stupid,
I
but,
think
like,
you're
that
right.
would
Oh
make
my
sense.
god, you're right. So are you really telling me they didn't think of that?
Trust me.
Wait. No, it can't be that.
Wait, who made it? Logitech?
Yeah.
There's no way they didn't do that.
No, and you know what? It's not the inversion left-right because this is left.
Yeah,
So it wouldn't be that inversion. I don't know what it is. I think maybe it's like if this is the back, then it's left and right for the back. It's the opposite. It's left and right.
Are you
No, it should be the same.
No, it would be the same.
No, that's wild. It should be the same.
So left is
So
left.
maybe it should, this thing should be flipped in some way. I have no idea. The camera should be this way.
Maybe.
My
Okay,
family
right.
were watching on the
The camera
Wait,
was
so
here. Yeah.
What if you just flip it like 180?
Yes, I think that's it. Yes. Okay, I don't think it can do that. I don't think it can do it. Yeah.
My name is
And that would
Margaret.
flip it.
Yeah. Interesting why. I gotta think about it. I have like reactive brain cells at the moment, so I can't figure out how to word this.
Margarine rat.
You know what's like?
Margarine rat.
Oh, actually.
My parents give her nicknames, but like we don't give her names. Actually, when I was like learning how to talk, one time I called her Lyssa and she's like, no, my name's Lyssa. And then I like diabolically smiled and started repeating Lyssa over and over.
That's the one that's
Like I've been a big
I know what it's.
I think that's a good one. If you can find a subsection of someone's But yeah, like if you have Christopher, like a subset of this stuff. If you want to spell Christopher, just go with the
That's what we're doing.
Just stop.
Alright.
My little brother, nappy boy, his brother.
Bye, Lisa. See ya.
What's his name?
No problem. Happy to help.
So not no
See ya.
relation at all. Also, if you want to stick out with
Yeah.
Thank you so much for doing that.
No problem. I'm gonna like, if I mean you're okay. You can always say if you're not okay with it. We usually post as part of the live stream. I was gonna say there was a lot of interesting stuff, but I'm gonna have to like rewatch it because I'm like half sleep deprived right now, so I feel like I followed half of it. But yeah, interesting. All right, we'll get started in like 5 minutes, so got a little bit more time.
Let's go, Khush, and let's go. Oh, I gotta have
Shut the hell up. Just because I'm naturally scripted doesn't mean it was you. Hey, nah. Who's that guy?
And OG pointer stick.
I'm a man. I have this big stick. First person swinging around.
Good thing we weren't recording that part. All right, we can even start early. Let me just save 2 things. Okay, make sure the slides work. Just make sure you share, if you can hit share screen, or join in the Zoom meeting. Yeah.
What's your reality? His matches might describe 5'10". Wears glasses. No facial hair, medium build. Here's the thing. Yesterday I was at work, so I was reading through it. I don't know how my bachelor's not there.
Like, I'm and I'm not gonna lie, like I said to my homie, who's like 4th year like, as well in Valentine, and he said, bro, I genuinely thought like it was describing you. I was like, dude, I'm really in Mississauga at work. I'll send you a photo right now. But,
Bro, I've seen him around. Shut up. What you're gonna do? You're gonna see campus security be like,
All right, we'll get started in like 2 minutes. Just make sure this works.
I want to sit up front so I can. You're gonna Google? Google him. Yeah, let's Google his name. Google and Google. What, Google and Google? Yeah. No, that's great. Google and Google. No, Google and Google. You're not seeing the vision. I see it. I don't see how. No, you Google them. Why don't you Google them before you see them? Because you can look at a picture of Google. So how do you?
All right, we're almost. Guess we'll start on time. Just a minute. It's kind of odd with the shadow right now. Yeah, we're 6:08 right now. Is the clock wrong?
Yeah, but I want to make sure that.
All right, we can get started. So our next speaker, Khush, let's give him a round of applause to welcome him.
Okay, hello everyone. My name is Khush, and my project is on can the compressible Euler equations be transformed into nonlinear Schrödinger type equations. Before I even start, my research would suggest that the answer is almost. So let's get started. So we start with a very basic question. What is a fluid? I want to start here because my project is not entirely a physics project. So it's good to stay grounded and talk about what a fluid is. So even before I start with what a fluid is, we know that the universe is basically a giant fluid. Everything in the universe is also almost a fluid. For example, liquids, gases, plasma. As we can see here, we have an aircraft wing, and we care about the turbulence with how the air goes over the wing, and we would like to simulate such a thing. We also care about the weather from time to time, so we can use fluids to simulate the weather. But from a more colloquial standpoint, a fluid is something that's allowed to flow. Right? We know intuitively that a fluid and a solid should be slightly different. And one way we can talk about fluids is by saying that the bulk behavior differs from whatever a solid is. Okay. So these are just some examples of where fluids are used. So this is turbulence and fluid dynamics, for example. And we can also see that, how blood moves in the brain and in blood vessels are also determined by whatever fluid equations we use. We also see that bacteria populations in petri dishes move under they move turbulently under whatever fluid equations we use. Another very cool example, in my opinion, is the accretion disk around black holes, because they're made up of hot plasma, and so we can also simulate those things with fluids. Okay. So let's now take a second to talk about the theoretical model of fluids. So what we're going to do is we're not going to think of fluid particles individually, because realistically, keeping track of the dynamics of that many particles is unrealistic. So in a mole of particles, we know that there's about 10 to the 24 particles. And so if you took any sizable chunk of fluid, there would be too many particles to really keep track of. And so what we're going to do is, relative to our scales, we can make the assumption that our fluid is a continuum. That allows us to, rewrite F equals ma in a very nice looking equation. And these are precisely the compressible Navier-Stokes equations or the compressible Euler equations. So let's talk about some of the terms before we move on. So this term talks about the compressibility of the fluid. Basically, how much in a fluid go in and out. So the easiest way to think about it is if you had this thing be 1, for example, then you know that fluid is, coming out of a source. If it was negative, you would know that the fluid is coming into that area. And so when we talk about the compressible fluid, we basically say that this term is, it could be 0, but in general, we allow it to be non-zero. A lot of simplified models of fluid dynamics assume that this term goes to 0, and that significantly simplifies the equations. For one, it gives you that the density must be constant. So that's already a nice simplification, because then we can move it out of this term, and so on. Okay, so now let's talk about the second term. So this is basically F equals ma. This is the F equals ma. One way to derive this equation would, be starting with conservation of energy and momentum, and then coming to these equations. But that's taking the easy way out, because we're assuming that fluids conserve momentum and energy and so on. There's a really slick way of deriving these equations by taking the Boltzmann equations, for example, and then taking second moments of them, and you would come back to the same set of equations. Okay, so let's start with the easiest term in all of this, and that is this rho F term. These are just any external forces that are acting on the fluid. The next simplest one is pressure, because this is just what we usually think of pressure as a thermodynamical variable. These other two terms sort of give you how the fluid is actually, how the velocity of the fluid actually interferes with the rest of the fluid. This term is known as an advection term, and it basically tells you how much is your fluid shearing or stressing. And finally, we have this S term. We can just ignore this for now. One last thing is we also have mu. This mu is the viscosity of the fluid. And in whatever we talk about, we will see that we will remove viscosity for now. And that's why we can just ignore whatever this term is. Okay, so let's now talk about some of the motivation of the beginning question, right? Why do we care about writing compressible Euler equations in terms of nonlinear Schrödinger equation? And the simplest explanation is, well, it's computationally expensive. For example, there are some, so the black hole picture I showed you over here. This one, if I remember correctly, took about 6 months to simulate. That is like an ungodly amount of time needed. And so if you wanted to do any research on blood thickening, for example, you would need to be able to do these simulations quickly, right? You wouldn't have 6 months to wait. So that's one very nice motivation, right? But why Schrödinger equation? Well, one of the things is we know from previous research that it's possible in certain limits, so that's a very simple motivation. But another one is quantum computing is booming. So why not use quantum computers? Because we know that in certain situations they're much faster. And this is why we also wanted to write it in terms of an equation that is inherently quantum mechanical, because we know quantum computers are very good at handling quantum mechanical algorithms. Okay, so let's now talk about some of the previous results we know. So if you assume that your fluid is pressureless, you basically get a very simplified equation, which if you've taken intro PDEs is called the Burger's equation. And we know that the Cole-Hopf transformation actually transforms the Burger's equation into a simple heat equation, which we know how to solve exactly. So a paper by Ayetekin took this idea and took the incompressible viscous Navier-Stokes equation into an imaginary time nonlinear vector Schrödinger equation. So here, psi is given by the curl of psi is actually the velocity. And the reason we can, have such a vector potential is because we know that in the incompressible case, the divergence of your velocity is 0. And so if we, think about what we did in ENM, it's obvious that we can write it as the curl of something. So you can, rewrite your equation to look something like this. And then we can apply this transformation. This is called the Cole-Hopf transformation. So basically it writes the components of the vector potential in terms of some quantity called theta. And then we arrive at the following very, very ugly equation. So I should mention that this T, so this is an operator that depends on the gradients of this theta function. And this is the Green's function for a certain PD. And so you can rewrite, this sort of looks like a Schrödinger equation if you really squint your eyes. So okay, we can do it in the incompressible viscous case. So what do we want to achieve? What are we even doing? So we want to start with the compressible Navier-Stokes equations this time. For now, we'll see in the assumptions I've removed viscosity. And so we want to take the second equation that we saw and rewrite it to look something like this. Spoiler alert, it doesn't really work, but it also does work, so that's good. Okay, so what are the assumptions we've made? So for one, we've assumed that the fluid is compressible, and so that means that all that means is this equation is allowed to exist. The second is we have no viscosity, so we can get rid of this entire divergence term. We don't need it. We have an isothermal equation of state. This is a thermodynamical assumption, and that just means that the pressure is linearly related to the density through something called the sound speed. Basically, it's the speed of sound in the fluid. And we can derive this equation by looking at PV equals nRT in isothermal, so in a constant temperature situation. And so basically all that means is we need this part to equal 0. Okay. So, well, I've just rewritten the equations here. And now what I'm going to now do something, again, from ENM, which is to write the divergenceless part. So we can firstly decompose the velocity into a divergenceless and a curlless part. In other words, we have a compressible and an incompressible part. The incompressible, we already know, can be written as the curl of something. And for similar reasons, we can write the compressible thing as the scalar, but the gradient of a scalar potential. We can then rewrite all of this into whatever this is. And now let's talk about the form of this. For one, let's look at the density equation. In the density equation, we see that there is no second order term in density. Okay? And even if we go back, even if we added in this divergence part, this adds in at most a first order density term. And so we can already conclude that the density equation will not really look like a Schrödinger equation given the transformation that we're using. Right? So we'll ignore this because we already know it's not going to work. Let's move on to the second term, which is the scalar, the vector potential. In this case, we do see many high order terms, so this is good. So in the Okitani paper, we don't have this coupling term, so we can get rid of this for now in our head. And we are left with this. This is very good because this is exactly what we get if we assume incompressible fluid. So, and we already know how to handle this term. This is, well, like I said, it's the Green's function of some nasty nonlinearity. And this is what that PDE is, right? So that's just our T operator, so we'll keep that. This term and this term from the scalar potential are good because now we can actually, define a special function and show that the momentum is still conserved. So assuming that we can write it as the curl of something and the scalar potential, the gradient of something, doesn't really break anything. And then we also have these many high order terms. Now one might ask, okay, why did I rewrite the equations to look like this? And my main motivation is I was just looking for terms that were, Laplacians and things, because the Schrödinger equation has a Laplacian term, and I wanted to get a Laplacian term after I took the inverse Laplacian. And that's why I have this term. It doesn't really mean much, unfortunately. Okay, so let's not actually do the transformation, right? So we have these three, one transformation from here, one from here, and three from here, so 5 in total. We can take the vector potential term and then rewrite it like this. Okay, very nice. I mean, it looks like something, I guess. One thing to note is it's not really a Schrödinger equation, right? This is something we will address coming forward. We can do a similar thing with the scalar potential and get something that looks like this. So if you see this term right here, this thing is so close to being a Schrödinger equation. We just have this, depressing natural long term, which we somehow want to get rid of. And that should be expected because if we notice, we see that this Laplacian term actually comes coupled with an extra g. So, it was futile from the start. But that being said, let's actually now, take a step back and compare everything to what we've done before. So, over here I've written, a nonlinear Schrödinger equation. And on the bottom I've written the equations we have. So we can see that, time derivative corresponds to time derivative. And this is what I meant by imaginary time. So you make a certain change of variable to get rid of this I dependency. And then we see that this t term corresponds very nicely to this. But now we have this, giant term that depends on, this is, this term comes from all the vector potential stuff, all of this, from this term. And the sigma term also comes from the same thing. Right? So why haven't I included this term as part of my potential? And the reason is really simple. We actually don't know what the form of this looks like. So in the Okitani paper, the reason the paper was actually, groundbreaking is because they showed that this Green's function for this PDE right here is actually well defined. Right? And because of that, it makes sense to write it as an operator on its own. So this is actually an operator that acts on psi and gives us a solution to this PDE. But we don't really know what the form of G is. All we really know is it takes in two different functions. So we actually have to look at a system of a couple of different PDEs. So in reality, we haven't really simplified our problem. We've just introduced new ones. But it's still good to see that, okay, part of what we wanted to do is still in what we did. Another thing you might notice is we have no Laplacian of psi term, right? And we conjecture this actually comes from the viscosity coupling. And so that is actually one of our next steps. So let's talk about future goals. So one of the first things, like I said, is we want to add back viscosity because we conjecture that the Laplacian term is actually coupled to the viscosity, and we can see sort of why that is from looking at the equation for what this Sij term is. It introduces some like second derivatives of psi, which is very nice. So that means we will hopefully get some Laplacian psi terms. Okay. The next thing we want to do is we want to look at the weakly incompressible limit and make sure that we actually get back the incompressible limit. So let's go back and see what we can change. So in these equations, a lot of things cancel out immediately, right? We can cancel this out, we can cancel this out, we can cancel this out, we can cancel this out. Right? So we get a more trivial equation for G rather than something that looks really ugly. And then we can assume that the density doesn't really change as much as we move. And then we can maybe see that it gets back to the incompressible limit. Next, we also want to add like magnetized fluids because my supervisors work in the astro department, and well, they look at accretion disks around black holes. So this is one question that they're really interested in: how do fluids couple to the magnetic and electric field? And we want to see if our procedure leads to any good research there. It turns out that you can rewrite E in terms of B in certain limits, and so that simplifies the Maxwell equations slightly. Next, we know also that B is incompressible, right? Because the divergence of B is 0. And so it's actually an almost trivial extension to the problem at hand. Finally, we want to simulate whatever we've seen and make sure that we actually get back to what we originally started with. And hopefully, we get that the amount of time it takes is not 6 to 7 months. Thank you. Are there any questions? Yeah?
Okay, so first thing, why work with these equations specifically? What types of fluids would you hope to simulate with what you've done? I know you said at the end it would be nice to work with
Like magnetized fluids?
magnetized fluids, but
Yeah, so let's go back to the start. So our fluid models, will hopefully simulate everything from how air goes over a wing of a plane to the weather, to blood flow in a thing, and black holes. So we have a wide range of things we want to simulate, and it turns out that all these things are governed by basically the same equation, right? Which is the Navier-Stokes equation, and that's why we care about the Navier-Stokes equation. Because with the black hole, all we really have to do is add in like a magnetic coupling, for example. So that's why we care about what equation we use, and it basically simulates all our models of the fluid. Every model of the fluid we have, in some sense, is a reduction of the Navier-Stokes. Yeah.
I'm wondering, is the structure of like any Navier-Stokes similar, or was there that popular? Like in other words, like if the analysis is really fun, then where's the flow from fluids?
Well, one place it already shows up is in the transformation, right? Because if this goes to 0, the transformation itself blows up. So that's one possible step. I'm not actually entirely sure if they map 1 to 1. I don't think they will. I can't tell you why I think that, but I just don't think they will. Because we at least hope that fluids behave slightly nicer than that. So I think the main blow up will show up when we do such a transformation. So it's important to look at what this looks like. Another assumption that I didn't actually mention is that our fluid sufficiently far away goes to 0, so the energy doesn't really blow up. So we don't expect energy blow-ups at least. Yeah.
Okay. So you said that fluids are on black hole.
Yeah.
Do you take into consideration the strong
already like baked into the.
No, so that's not baked into the theory whatsoever. So when we talk about, like in the future goals, when I talk about the magnetohydrodynamical equations, those are literally just the Navier-Stokes equations coupled with, like, it's as if a electrically charged material is moving. So they don't take into account any gravitational terms.
But Ayetekin gravity, like, anything, or like.
I mean, yeah, of course. Because like, gravity is also highly nonlinear. One thing about Maxwell equations is that they're very linear, so then they don't add too much extra complexity on top of whatever Navier-Stokes is.
I'm just asking like black hole.
Yeah, around black holes things go really crazy. And that's also one of the reasons why it takes so long. It's because like, simulating most things is not numerically stable. Right? And so you have to sort of find the perfect balance between can I do realistic like time scales? If I do realistic time scales, I can no longer do realistic like length scales, right? So that's also one of the questions we hope to, give an answer to. It's like we want to be able to do both of them simultaneously. So a quicker algorithm will hopefully, push us one step closer to that. Yeah.
So at the beginning you talked a lot about turbulence, and then kind of never really touched on anything. Could you go just expand on why you care about turbulence and what that has to do with you?
Yeah, okay, so that's actually a very good question. I don't care about turbulence. All of this actually comes from a grant my supervisors put in. They also did mention not to put this picture in precisely because of that question. So yeah.
That's precisely why I asked.
Yeah, no, I don't really care much about turbulence, but turbulence is a byproduct of the Navier-Stokes equations, at least mathematically. So that's, and I mean, turbulence also gives us a hint towards the fact that possibly the Navier-Stokes equations don't have smooth solutions because turbulent fluids are inherently non-smooth, and we do see turbulent fluids. So either our models are wrong or our math is wrong. Yeah.
If you consider finding the market onto other like quantum mechanical equations like involving the
Did we do that? As of right now, there's no need to, at least in our thing, because we are coming from the perspective that, okay, someone's already done it for the incompressible case and with the Navier-Stokes equation, so we just want to see if we can move it forward. Right? So we didn't really consider that, but, and most, I might be wrong here, so please correct me if I am, but most quantum computers don't really, they're better with not like a Schrödinger equation than Klein-Gordon. So, yeah, it's just and it's also a nicer equation to look at. So, that's another reason we would want to do that. So, yeah.
Then you also made like some considerations for like that the equations would actually be like easy for the quantum computer to compute in the form they are as founded. I used to like playing around trying to convert it into Schrödinger and put it into other like CS and PhDs in the power.
Okay, I'm glad you asked that. So if we go to, let's see here. So in the incompressible case, this T operator is actually not, okay, when I say it's not horrible, it's not as ugly as one might think, because this nonlinearity is actually not that bad. Like if you do some simplification using things you learn in PDEs, you will arrive at a form of the T operator that is not disgusting. However, this the scalar potential is where the actual issues lie, right? Because we have a bunch of like weirdly coupled derivatives, right? That don't necessarily simplify nicely, and so it will be an uglier looking equation, right? But we can't even, as of right now, we can't really say anything about whether it's easier for a computer to do this because we don't know what it looks like, right? We know it has to be the Green's function for this, but that's not too useful for a computer. So we haven't actually even reached the step where we can ask that question.
That's all the questions. Thank you very much. We're good. All right, thank you for coming, everyone.